Hello and welcome. We are looking at reflections. Okay, so just like translation and dilation and rotation, I'm going to be showing you this slide here that defines pre-image, image, and isometry. Now, pre-image and image are the figure before and after the transformation of some sort of object or point or set of points or whatever. So in this first example here, you have a pentagon that has A transposed to A prime, B to B prime, etc. This is an example of a translation where every point in this object is literally shifting down to here. It's basically the same exact thing. B is congruent to B prime as far as angle B is congruent to angle B prime. Segment CD is congruent to segment C prime, D prime, etc. That's a translation. Here's reflection, something we're about to do more of here. If I reflect across this line here, this axis of symmetry, Q goes on to Q prime, R to R prime, and P all the way down to P prime. It's like a mirror image of itself. If you tilt your head to all the way 90 degrees to a side, you'd kind of see how one is symmetrical to the other. And then here's a rotation where you actually see these points rotating here. You can see Y go all the way down there to Y prime, and Z only goes down to Z prime there, etc. So the object rotates about 90 degrees. All three of these types of transformations, that is translations, reflections, and rotations, are all isometries. And that is when the pre-image and image have congruent corresponding parts. So as I mentioned in the first pentagon, all angles and segments which correspond to one another are congruent. Well, that's the same thing here as well, and it doesn't matter if the colors are different, or if it's oriented a different way, or if it's a reflection of the other thing. They're still the same size, and I could map this back onto its pre-image. So again, the pre-image is before the transformation happens. The image is after the transformation happens. And these pre-images and images are all isometries. The one that's not an isometry is a dilation, and you can see an example down here. There's an upward facing arrow here, and when I dilate it, I basically grow its size. And here's an upward facing arrow here as well, but now this segment is no longer congruent to this segment. Even though the angles, like these two angles here, might be congruent to each other, these might be 90 degrees, the segments are no longer congruent, so they do not fit the definition of isometries. So while translations, reflections, and rotations are isometries, dilations are not. So let's look straight at reflection, though. I'm going to read off some of the stuff up here, and we'll do some examples. A reflection is the flipping of an object across a line. I'm going to call it the axis of symmetry. I might interchangeably use the phrase line of reflection, which makes just as much sense. And all corresponding points in the pre-image and image are going to be equidistant to the axis of symmetry. And distance is measured perpendicularly to the axis of symmetry. So just so you're aware, the shortest distance between a point and a line is the perpendicular line for that. For instance, anything else is just a little bit farther out, if not much farther out. So whenever I refer to distance, I am talking about the perpendicular line. So the good news is we will be looking at a whole bunch of lines that are either vertical or horizontal. So when we find the perpendicular line, it's going to be very easy to count, and it'll be very easy to find because it's just going to be the opposite. If the axis of symmetry is vertical, then the line drawn perpendicularly to it is horizontal, etc. When it's not horizontal, that's when we're going to be doing some other nice fun stuff there. So let's do this first example here. You're actually going to do two reflections. We'll do one and then the other. I'll actually name both of them so you're well aware of what's happening. Okay, so first we're going to reflect point A across the y-axis. Now the y-axis is this guy right, whoops. The y-axis is this guy right here. Okay, so when I reflect it across it, what I really want you to think about is if A was looking into a mirror, and on the other side is mirror world. Now if you look into a mirror dead on, because this is all about perpendicular, like this right here, how far away, where is the other point, and how far away is the other point? So the other point is 1, 2, 3, 4, 5 units away from the axis of symmetry, just like point A is. So here is A prime, 1, 2, 3, 4, 5. So A prime exists at the point -5, 5. These will be best done by graphs. I'm not only going to do them mathematically. a graph will always be used, and it's always recommended that you do use one, especially when you're referring to a line that you have to draw and count how far away it is. So there's A prime, but I'm also going to do this next part. I'm going to reflect it across the x-axis as well. What I mean by that is after this, I should just put a comma and say, let's take A prime and now reflect it across the x-axis. So I'm going to take this new point right here and do exactly that. Here's the x-axis. And just so you're well aware, because we're going to be doing more equations, the y-axis is the line x equals 0. The x-axis is the line y equals 0. So if it asks to reflect across x equals 0, then y equals 0. It's the same thing. So the same thing here, as I go down 5 units to find the point that it is crossing through into mirror world, I go 5 down one more time, and I will find my next point. I'm going to call this one A double prime, so it has a new name. And that's going to be my final answer at -5, -5, because that satisfies all that was asked for me to do. So this is the reflection across the y-axis, then across the x-axis, and this is just for one single point. And this composition of reflections is actually kind of cool because no matter which order I do it in, it's commutative, meaning I could have reflected across the x-axis first, then across the y-axis, and I would have gotten at the same point, which is kind of nice. Okay, now let's take an object. This is quadrilateral ABCD, and we will reflect it across the line x equals 2. So whenever you do these things, my recommendation always is to draw that axis of symmetry first. Now this one's very interesting because in this one, not only are there multiple points, but everything is going to reflect across this line. Now, as I think you would normally assume this happens, is that not a part of your image, pre-image, should be in mirror world already. So if I'm looking at point A, and I want to reflect it across x equals 2, I'll count 1, 2, 3, 4 over. And here's 1, 2, 3, 4 over this way. Here's A prime. Now A prime is in mirror world, but so is point C. So that's kind of weird that it's over there. But C is just going to go on the other side. We'll do that in a moment. Let's first do B. 1, 2, 3 away. So here's B prime, also 3 away from the axis of symmetry. Now point C, already in mirror world, will go over on the other side. It has its own kind of mirror world. That's also 4 units away. There's C prime. And D prime is on the line, so its image is also on the line. So it just looks like that. So if I connect these points here, A prime, B prime, C prime, D prime, I should also write that that's D prime, connect like so. And D prime, once again, is right here, just as D is. So as you take a look at this, if you kind of look straight down right here, you should see that symmetry happen. It's not just at the vertices, it's at literally every point. What if I wanted to reflect this point across? Well, it's about 2.5 over, and boom, 2.5 over. There it is. But when I connect the sides, the segments, they are already assumed to have reflected, just like that as well. So we've made that reflection, and as you can see, it overlaps with the image and pre-image overlap with one another, but you still get that symmetry that you're looking for. Okay, the third example is one where you are given the pre-image as a drawing, or as the points are plotted, and then you're given the image A prime, B prime, C prime as its vertices, and we have to find out what the axis of symmetry is that describes this transformation. So in this particular instance, like I said, it's always good to graph, but this time we have to actually graph the other points for A prime, B prime, C prime. So A prime's at -6, 7. And this one, they're telling us it's a reflection, so I think you can sort of start to see what's going to happen with it. B prime is at -1, 7. It's right here. And C prime is at -4, 9. 7, 8, 9. So it's up here. So if I connected these, I have the image of the transformation of a reflection from this pre-image. So we have to find the axis of symmetry. And we have to write the equation for it. So if I did a reflection and C got mapped to C prime up here, etc., and you see that segment AB is parallel to segment A prime, B prime, you can sort of start to make a guess that, well, you're reflecting somewhere over here. We got to find that line. Now we know it's a horizontal line, because A goes straight up to A prime, which means the perpendicular line is that axis of symmetry. Let's go ahead and determine what that is. And what better way to do it than to literally count? If you think about the previous example here, when I counted from A to A prime, I said, how far away am I to my axis of symmetry from A? Okay, cool. The image for A prime will be the exact same distance away. But from A to A prime, that whole distance is twice as long as the distance just from A to axis of symmetry or A prime to axis of symmetry. So what I'm going to do in this example here is let's take a look at the distance between A prime and A. So that's 1, 2, 3, 4, 5, 6, 7, 8 away. So if this is 8 away, half that distance for 1, 2, 3, 4 right here is where my line should be at. Let's confirm that with some other ones. B and B prime are also 8 away. So 1, 2, 3, 4 up will give you the same thing. And C and C prime, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 away. Half of that, 1, 2, 3, 4, 5, 6, should also be the same distance. So it looks like this axis of symmetry is all falling right here on the line y equals 3. So it's going right across there. So that equation is y equals 3. We're actually good to go. That's all you need to do. But again, it really helps getting that graph first, recognizing what you're dealing with, and then basically counting half the distance between any point from pre-image to image. Okay, the final example here that I'm going to give you is based on this highlight right here. When the axis of symmetry is not horizontal or vertical, the line perpendicular to it can be found by finding the opposite reciprocal slope of the axis of symmetry. And the distance can be equated using a rise over run ratio. I'll be sure to get back to that in just a moment. So this one here, we're just going to use one point, reflect negative 6, 2, negative 6, negative 2, across the line, y equals negative 2x plus 6. So what's going to happen here is this is point A. I'm going to reflect it across the following line. I need to start at 6, down 2 over 1, down 2 over 1 for negative 2 over 1 slope. And I'll go ahead and draw this line because this is now my axis of symmetry. So this one right here, I need to go perpendicular to it. And unlike a vertical line, this is just going to be a little bit more of a hassle because now I need to make sure that I create an opposite reciprocal slope. So there's about my line. I can make it a little bit closer. Okay, so here with A, this point right here, I need to say that the slope of this line here is negative 2 over 1. So the opposite reciprocal slope of that is 1 over 2. Once I use the opposite reciprocal slope, let's draw the line that goes through A that has a slope of 1/2. So I'll go up 1 over 2, up 1 over 2, and keep doing it until you find a possible point of intersection. And there's one, and I landed on one perfectly. That point is 2, 2. But I can keep going because I'm going to be making, not really making a line here, but what I do need to do is find out where A prime is. So this is where my distance will be equated. I don't necessarily need to find this distance, and better yet, I'm definitely not going to count it. But what I can do is say, how far did I rise? How far did I run? However much I did, I have to repeat that again. This is just like when we found, this is just like finding the midpoint, or being given a point and you find that midpoint, and then you have to find that other point. You just have to double the length that you went. So if I go up 1, 2, 3, 4, and I run 1, 2, 3, 4, 5, 6, 7, 8, I have to do that one more time from the point 2, 2, and I will find this new point called A prime. So that point is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over, and 1, 2, 3, 4, 5, 6 up. So my A prime point is at 10, 6. And again, mathematically, it's the equivalent to midpoint. Once you find what that midpoint is across the axis of symmetry, I had to do 2 plus 8 and 2 plus 4. From 2, 2, I rise 4, run 8. And that'll give me that final point right there. And again, the whole idea was I needed to make sure that I was running perpendicularly to it. That was by finding opposite reciprocal. And that all started by graphing this first. So a little bit more to do, especially if you have multiple points to do it, but if you do it with a bigger graph and you tilt your head over to the left and you say, yeah, that looks symmetrical, then I think you're in good shape. Fine.